Hello, everyone. So we're going to take a look at some wave interference in this video. What I have plotted here with this red line is a wave, and this is wave 1. And this wave has a period of 2 seconds, which you can't see that in the wave because this vertical axis is the y direction. So that's the displacement, say, of a particle. And the horizontal axis, that's the x-axis, that's distance. And so this is just like a snapshot in time. But I have the wavelength, this program I'm using, Desmos, it doesn't allow you to use Greek letters. So I just have L for wavelength of wave 1 is equal to 2. So you can see this wave, here's a crest, and we go over here to the next crest, that's 2 units. And to the next crest, that's 2 units. And it has an amplitude of 1. Okay, so this wave has an amplitude of 1. So from trough to trough is 2 units, trough to trough, and from this point to this point is 2 units. So it has a wavelength of 2 units. As a period of 2 seconds, so if I move time forward, you'll see that the wave will travel. See the wave moving as time advances. So now we've moved 1 second, and so half of the wave has moved. So we were at a crest at time at x equals 0. Now we're at a trough at x equals 0. And if we move time forward 1 more second, we see that 1 full wave has passed by. We're back with a crest at x equals 0. So every 2 seconds, 1 wave passes by. All right, so we can see the period. If we change the wavelength, right, the wave becomes twice as long. So now from crest to crest is 4 units. And if we progress time, we can see the wave traveling, and it has a longer wavelength. If we put the wavelength back to 2, let's say we change the period, make it shorter, right? What happens now is it takes less time for the wave to travel. Now to compare that, if I move the time at a constant rate, see the wave moving. Okay, if I rewind it, if I make the period 2, you can see it's moving slower. And if I make the period, say, 4, it'll move even slower. Because it takes 4 seconds for 1 wave to pass through. Okay. Now, if I put a second wave on here, the blue wave, let's do this. Let's have it move in the same direction. And let's give wave 2 a period of 2 seconds. So now you'll see that wave 2 is moving. It's the blue one. The blue wave, it moves faster than the red wave. Why? Because it has a shorter period. It means a higher frequency. Where if I give wave 1 a period of 2 seconds, then the waves will never separate. They'll be the exact same. However, if I make the wave 2 travel in the opposite direction, you can see that they do separate because they're traveling in opposite directions. And so we'll start with that. So you see these waves, they travel in opposite directions. Right now they're in phase, right? The crests are aligning and the troughs are aligning. And here they're out of phase. The crest of one wave is aligning with the trough of another wave. Now I'm going to plot a third wave that is just the sum of waves 1 and wave 2, and that's the green. And so this is the actual wave that would, if these two waves, wave 1 and wave 2, were, say, in a string or in air or whatever, the actual wave you'd observe is the green one. It's the interference of those two waves. As time passes, so right here at time t equals 0, we have complete constructive interference. As time passes, you can see that the resulting wave gets smaller as the waves slip out of phase. And here they're completely out of phase, and you can see the resulting wave is just flat. It's complete destructive interference. Right? And so if we play this, we can see it oscillates back and forth. Now, if the periods of the waves are different, let's say wave 2 has a period of 4 seconds instead of 2 seconds, you'll see it'll look a little bit different. Okay. Waves can travel in the same direction and also interfere, as long as they have a different period. Oh, that's going backwards in time now. So you can see how the waves constructive interference and then destructive interference. Constructive and destructive. What if the waves have different wavelengths? So I'm going to make the wavelength of wave 2. So we'll have the same period. We'll give wave 2 double the wavelength. So now you'll see, because they have different wavelengths, we never achieve that complete destructive interference. And the resulting wave, the green wave, it takes on this kind of like a more complex nature as those waves interfere. And we can actually just see the resulting wave itself. So when you see, music is a bunch of waves interfering with each other. So you get, these complex sound waves, which you can see these complex sound waves are created by multiple sound waves of individual frequency and wavelength interacting with each other and interfering with each other. And so as instruments produce sound waves at different frequency and wavelength, they travel through the air and they interfere with each other to make more complex sound waves. Even if we change the period of one of the waves, it'll look even different. So this is the resulting wave from the interference of waves 1 and wave 2, which will bring them back up here. All right, so you see them interfering with each other. So we can't achieve complete destructive interference anymore because the waves have different wavelength. If they have the same wavelength, it's still possible. Right? So only waves that have the same wavelength can achieve that complete destructive interference whenever they're completely out of phase, like right here. And that's if they have the same amplitude, right? If one of the waves has a different amplitude, say if we double its amplitude, then we'll never be able to achieve complete destructive interference either, because one wave is double the amplitude of the other. So you see the resulting green wave never drops to 0. It just reduces in size. So that's wave interference. We could see wave interference if we simplify it back down. Say 2 waves traveling in opposite directions. So, let's make the amplitude the same. You can see that wave interference. Now we have 2 waves traveling in 2 different directions. And you can see constructive and destructive interference. So there's very different scenarios where the waves can be traveling in the same direction, have different frequencies or periods, or traveling in opposite directions. But the resulting wave in a medium is the sum of all the waves traveling through the medium, and that's called interference. And you can have destructive interference, like in this case right here, where the waves negate each other because they're out of phase. You have constructive interference, like here, where the waves add together because they're in phase. Thank you very much.